A literary critic wants to establish that the mean number of words per sentence appearing in newly discovered short story is different from 9.1 words. A sample of 36 sentences provided the data with a mean of 8.6 words and a standard deviation of 1.2 words. Test at a level of significance alpha is equal to 0.10. Okay, so notice that this is a null hypothesis testing example. So null hypothesis, we label it as H subscript null, is the hypothesis that you're going to nullify, that you're going to reject. Okay? You're going to reject it because that's basically what it's for. You have a null hypothesis and it's meant to be rejected. The only thing that happens if you don't reject it is if you fail to reject it, right? You don't have enough information to reject it based on your observation. So you get your statistic. If you fail to reject it, that's it. You don't reject it. But you should always assume that you will try to reject it based on the observed values that you get. So the null hypothesis in this case is that the mean is going to be equal to 9.1, right? Because the suspecting literary critic here says that I think that the mean number of words per sentence in the short story is different from 9.1, right? So that's can be labeled as the alternative hypothesis. Now, different means not equal to 9.1, and not equal to means it can be greater than 9.1 or less than 9.1. And to accommodate that at the same time, we use not equal to sign. Okay? So notice that you've probably heard that null hypothesis tests can be one-sided, right? Either the right-sided, left-sided, or two-tailed test. In this case, it's a two-tailed test. As you can see, I'm assigning the rejection regions equally on both sides because this is symmetric distribution, and I'm using a two-tailed test. And the rejection regions start from a certain z-value that we should find out what that is, okay, based on the level of significance. And how do I know this is two-tailed? Well, I know this is two-tailed because, like I said, this can go into either direction, right? The mean can be greater than 9.1 or less than 9.1. So to accommodate that at the same time, these both possibilities, we have to use a two-tailed test. So we have to divide our rejection regions of 10% equally among two different parts, right? So 5% on the left and 5% on the right. And the rejection region starts at a certain negative z-value or a certain positive z-value and above, right? So if we go certain z-value and below, we're the rejection region. If we wind up in the observed statistic at a certain positive z-value and above, we're the rejection region as well, right? So we have to get an observed z statistic from the given information, okay? So let's do that. Notice that once again the alpha level is 0.10. And notice that here I'm labeling the z at the alpha over 2 because we divided the rejection regions into two equal parts. Okay, and just to remind you that if the observed z statistic is in the rejection region, either this one or this one, we will reject the null hypothesis and conclude that it's not equal to 1. The mean number of words per sentence in this short story is not equal to 9.1 words. Right, so we have to test that statistic. So alpha divided by 2 should be 0.10, 0.10 divided by 2, which will give you 0.05. All right? So basically, what it means is that the z-value of 0.05, or namely this one in this case, alpha over 2 is 0.05. So the z-value here means the z-value at the 95th percentile of this area here, right? The 95th percentile. So the 95th percentile means that, remember that you start the probability from 0, from the very beginning of the graph, and you go all the way until the z-value at the 0.05. So 0.05 means the remaining probability in the probability table, the remaining 5% until the very end, until you reach 100%. Right? So this is the 95th percentile of this entire graph. So to find the z-value of the 95th percentile, we basically look at the normal table. Notice that the z's start from 0. This is the positive z table. You see the z's are positive here from 0 all the way to 3.4. And the z values here are also positive. These just give you hundredths places of the z, and these give you the tenths places, right? The whole numbers and the tenths places. And you have to add these up, of course. You have to add the whatever probability that you're looking at in the table. You have to find the respective row value of the z and also the respective column value of the z. You have to add them up because that will be the complete z value. So in this case, we're looking at 95th percentile. So that means we're looking at the 95% probability. And this is about this one here. Anything else is greater or less than, but this is not exactly 0.95, but this one is equally away from 0.95, as you can see by the numbers here, just as this one is. So if we get the average of these two, we'll find the exact z value that we need. Notice that these two values correspond to the row z value of 1.6, right? So let's label that 0.05 is going to be what? It's going to be the average of, so let's label 1.6, 1.6 plus, so this one will stay because these two values are on the same row, but then the top two z values, the hundredths places that I was just talking about, that you have to add to the column z, whatever in 1.6 in this case. So you have to add these two because they correspond to these two values. So adding these two and finding the average. So 0.04 plus 0.05 and divide that by 2. So what you get is 1.6 plus, and the average of these two will be 0.9 divided by 2. And right, so that's going to be 0.045. And if you add these up, you will get 1.645. Okay, so that's the z value that we found that corresponds to exactly the 95th percentile in this probability table. So notice that if you go all the way to the highest z possible, you will get to 100%, just as the area is meant to get. So you start from 0, that's why you will see negative z's until we arrive right at the middle. And right at the middle is the mean, where the z should be 0, right? That's where it changes the sign. The z becomes positive. And that's exactly what you witnessed here. The z is 0 when the probability exactly 50%, right? When exactly half of the area is already covered, right? It starts at 50% and covers the right 50% on the right side of the mean until it gets to the 100%. So you can see that it makes sense with what we found. Right, so the 95th percentile was, again, 1.645. 1.645. Beautiful. Okay. Okay, now the next part is going to be finding the sample mean. Well, the sample mean is already given to us. It's 8.6. And the standard deviation of the sample, now notice standard deviation of the sample is 1.2. And the number of items here is going to be 36. The number of items in the sample, number of sentences in this case. So now we know that the observed statistics, first of all, let's write the rejection. Rejection z statistic. The rejection z statistic happens when the z is less than or equal to negative 1.645, or when z is greater than or equal to 1.645. So what this means is that we already found that the rejection z is 1.645. It's going to be here because we found that was a 95th percentile, right? We just found that here. So 1.645 and above will be the rejection region. That's why z is greater than or equal to 1.645. But due also to symmetry, since we have another rejection tail here, region, we know that the negative z is going to be such that z is less than or equal to the negative of 1.645, right? So if the observed statistic that we gather from this information will exceed or be the same as 1.645 or be below or the same as negative 1.645, we know that we will reject the null hypothesis because we will know something's wrong with it because we're in the rejection region, and we will just reject it and conclude that the mean time is not equal to 9.1. All right. So let's find the observed z statistic. So notice that the formula to be used for this is going to be, so observed z statistic. So observed z-statistic, we know the formula is mean, sample mean minus the alleged mean divided by population standard deviation divided by the square root of the sample size. Now, we know, you might say, but you know the sample standard deviation. How do you know the population standard deviation? Well, you know that actually, since we're talking about a sample of at least 30 items, we know that the population standard deviation can be approximated to the sample standard deviation. Okay? So we know that, right? And this is equal to 1.2, right? So we know that the population standard deviation is about 1.2. So we can go ahead and do this. We will get 8.6 minus 9.1 divided by 1.2 over square root of 36. All right. Okay, so what this should give us is exactly negative 2.5. So notice negative 2.5 is going to be at the left rejection region. Okay. Now notice that, why is that? Because negative 2.5, so we're going to say since negative 2.5 is less than, not only equal to the start of the rejection regions on the left side, not only equal to minus 1.645, but actually even below it, right? It's below negative 1.645. We know that there is sufficient evidence to reject the null hypothesis and conclude that the mean is not 9.1. Okay? So now the second method of rejecting the null hypothesis and concluding it is to find the p-value, the corresponding p-value at which the observed z-statistic began. Okay? So notice negative 2.5 has a certain p-value next to it because we know that the value corresponding to the rejection z's that we found was 10%, right? This is where the rejection regions start. But actually the p-value that corresponds to the observed z-statistics is going to be even smaller than the 0.10, right? Because the z-value, the observed z, was way less than negative 1.645. So we were somewhere here. So the p-value, let's say this would be negative 2.5. The p-value would be the region shaded on it and to the left. And the same thing on the right side. This would be 2.5. And everything to the right of this point would be shaded, right? So it would be a smaller region, even smaller rejection region, part of the rejection region, but even smaller, and totaling that would give you the p-value. Okay? So let's find that p-value that corresponds to the observed z-statistic area. So the p-value, and notice what the p-value means. The p-value is basically the probability that assuming the null hypothesis is true. So let's say that we assume that the mean is 9.1. What is the probability of having a observed z-statistic of negative 2.5? So basically, if the null hypothesis is assumed true, it is an extremely unlikely event that we should be at the observed z-statistic as where we are, right? And if we wind up there at this extremely unlikely region, that means something is wrong with the null hypothesis, right? Because this is extremely unlikely, judging by the graph, right? And it means that something's wrong with it and we should reject it, right? So this is what the p-value is, the probability of having the observed z-statistic and less, right? Extreme or even more extreme than the observed z that we got, right? So we sum up the areas to the left of this negative 2.5 and to the right of this 2.5. We add them up and we find the p-value, right? So notice that in order to do that, we have to use this part. We have to use the negative 2.5 and kind of go in reverse using the table. So remember that we started we started finding using the probability the corresponding z-value. But here we have to do the opposite. We have to first use the value now and find the percentile, right? So negative 2.5. Notice that you might be stumped. You might say, but these are all positive z's. But once again, don't be thrown off by this. Because negative 2.5, just as I said, notice that this is 2.5 because of symmetry, right? Normal distribution is symmetric with respect to the mean. So that means if you are talking about negative 2.5, you can look up 2.5, the positive 2.5 in the table, and find the remaining probability on the right side, right? Basically find the percentile and find the remaining probability. So 2.5 is what we should be looking at. And notice that this is this. And notice that we're only looking at this value here. We're not looking at the other values for the probability. And because 2.5, notice that 2.5, this row number corresponds also, this value corresponds to this column value of the z, because 2.5 is equal to 2.5 plus, remember that I said that these have to add up. The row should add up with the column number of the z's. Notice that adding the 0.00 does not change the statistic. It is still 2.5. That's why we're stopping at this value. We're not looking at any other values on this row, any other probabilities here. Right? So 2.5. So to find the p-value, we need to subtract this value from 1. Because remember that we're talking about the rejection, the remaining probability to the right of the 2.5. Z value, right? The remaining probability to the right of this percentile z that we found, right? So we have to subtract this value from 1 to have the remaining probability, and that's about 1%, less than 1%. But here's another tricky thing. We have to multiply this value by 2, right? Because we're talking about this shaded region to the right of 2.5 and this shaded region to the right of the negative 2.5, right? So that's why we have to multiply this by 2. And I just said that we have to find the remaining probability to the right of this 0.9938. So we have to subtract 0.9938 from 1 because we know the entire graph is 1. 100% is equivalent to a number 1, right? Because the probability is never greater than 1. The highest probability is 1. So you have to subtract all the probability to the left of this 2.5 from the beginning of the graph to this point. And that's going to be the remainder. That's why I'm doing 1 minus that, right? 1 minus the probability percentile at the 2.5, which is 1 minus 0.9938, right? Everything to the left up to the point of z 2.5 is the probability value corresponding to 0.9938. That's why we have to subtract it. 0.9938. And again, why did I multiply this by 2? I multiplied by 2 because I'm not only looking at this region to the right of 2.5, the remaining probability, but also this one, right? So not to forget that we need to have the second one, which is exactly the same region in probability-wise and area-wise, the same region as this region when we're measuring the area, right? 2 of these areas equally. That's why I multiplied this by 2, right? So if you do this correctly, you will get 0.0124. And notice that I said before that this p-value must be less than, the total p-value must be less than the alpha, right? The rejection, the total rejection region of 10%. Notice this corresponds to 1.24%, right? A little more than 1%, smaller than 2% in total, right? So this is such a small p-value. As a result, here's what we get. We know that this is definitely smaller than the alpha, which was equal to 0.10. Okay? So that's another way of showing that we have to reject the null hypothesis because we landed at an extremely unlikely probability there, right? We landed at extremely low probability assuming that the null hypothesis is true, right? If you're arriving at such a small area, you definitely know that something is wrong. It's smaller than the alpha. At this level of significance, 10%, the null hypothesis must be rejection, right? So we can say sufficient evidence to reject the null hypothesis at the 10% significance level. Alright, so I hope this was useful. Thank you so much for watching. See you in the next video.